Hello, AP Chemers. We are going to talk about three more laws when it comes to gases today. So the first one is Graham's law of diffusion and effusion. Let's first define what diffusion and effusion mean. And they're basically just movement of gas particles. So diffusion is when you have a gas moving through another gas. So movement of a gas through another. Effusion means the movement of a gas through a small hole or a small opening. So, movement of a gas through a small opening. So, basically, Graham's law talks about the movement of gas particles. And Graham's law says that the rate of effusion or diffusion is inversely proportional to the square root of its molar mass. So let's write that down first and talk about why or how. So the rate of diffusion or fusion of a gas is inversely proportional to the square root of its molar mass. So let's say you have two gases at the same temperature. What would be the same for both of these gases at the same temperature? Well, their average kinetic energy will be the same, right? So for two gases at the same temperature, if you have the same T, then they have the same kinetic energy. Or average kinetic energy, I should say. So remember that average kinetic energy is half mv squared. So we're going to say that half mv squared of gas 1 is equal to half mv squared of gas 2. You can cross out the halves. So you get this right here. And then I'm going to move my v's to one side and my m's to the other side. So if I move my m here, it's going to be at the bottom. If I move this v here, it's going to be at the bottom. So you're going to get this. And then if I take the square root of both, I get v1 over v2 is equal to the square root of m2 over m1. So v is the velocity, right? So the speed or the rate. And m here is mass, but it actually stands for molar mass. So notice that it is inversely proportional. So 1 and 2, but then 2 and 1. So that tells you that the higher molar mass, the slower the speed. Which makes sense because if you, let's say, try to run a mile right now versus if you put on a really heavy backpack and then try to run that mile, the heavier you are, the slower you're going to be. Or, for example, when I was pregnant and I gained like 70 pounds, I could barely walk. I was kind of wobbling. I was going very, very slow. So the heavier you are, the slower you are. So same thing with gases. The heavier they are, the more massive they are. So the higher the molar mass, the slower they're going to be. And so the rate is inversely proportional to the square root of the molar mass because of that square root here. So that's what this is saying. This is the same thing here. It's the rate of effusion or diffusion of gas A in relationship to gas B is going to be equal to the square root of the molar mass of gas B over gas A. So again, that inverse relationship. And because of that, it's the same way with density as well, because if you're given the same volume, you have the same number of particles, and so the molar mass of them would be different, and it would be the only difference between the density versus the molar mass because they have the same volume. So you could apply this to density as well. So on the AP exam, I know last year we used this equation here or this equation, which are the same thing. This year you do not need to use the equations. They're not on the equation sheet. You do not need to use them quantitatively. You are responsible though for understanding this qualitatively. So basically they won't ask you to calculate anything, but they will ask you to either determine which gas would move faster, or based on the speed, which gas is lighter, based on this relationship here. So you need to know that the lighter gas particles effuse or diffuse at higher rates than heavier gas particles. That's really all you need to know for Graham's law. Okay, the next law that we're going to talk about is not new. It's Henry's law. We also talked about this last year. And so Henry's law says that the higher the pressure, the higher the solubility of a gas. So the higher your pressure is, the higher the solubility. So think of two soda cans. One is closed and one is open. Remember when they make the soda cans, they apply lots of pressure to keep the carbonation in, and then they seal it. So then when you get it home, if you open it, you hear that hissing sound. That means the pressure is equalizing. So the extra gas particles that are in the can are going to escape to equalize the pressure, so the pressure goes down when you open it, right? So the closed soda can is under higher pressure than the open soda can. Now, if you were to take a sip of both, so open it when it was closed, right away take a sip, versus open it, leave it out for the pressure to equalize, then take a sip, you're going to notice that the closed soda can had a lot more carbonation. You feel more carbonation than the one that was open and let to sit. And so that tells you that with more pressure, you have more solubility of that carbon dioxide in your soda. And so the higher the pressure, the higher the solubility. So again, you need to understand it qualitatively. The relationship between pressure and solubility of a gas is direct. The last law that we're going to talk about here doesn't really have a name, but it has to do with the temperature and the gas solubility. And basically, the higher the temperature, the lower the solubility of a gas. So the higher the temperature, the lower the solubility. So it's an inverse relationship, and it's the opposite of the solubility of a solid typically. So most solids, not all, but most solids, if you increase the temperature, you can dissolve more. With gases, if you increase the temperature, you dissolve less, always. And again, think of two soda cans. One that you put in the freezer, or in the fridge, so it's really cold, and then the other one you leave out at room temperature. If you were to open both up and take a sip of both, you will feel a lot more carbonation in the cold one than in the room temperature one, or the warm one. So the gases, the CO2 gas, dissolves much better at a lower temperature. So the cold soda has more carbonation, or more gas particles dissolved. The reason for that is the movement of the solvent particles. So in a cold solvent, the solvent particles are moving kind of slow. So not very many of the gas particles get to the surface and escape. Whereas in the warm soda, the solvent particles are moving kind of fast, and so they carry with them those bubbles, those carbon dioxide pockets, and they carry them to the surface, and once they get to the surface, they escape. And so your soda becomes flat. So the colder the temperature, the higher the solubility, or the warmer the temperature, the lower the solubility of a gas.